We will continue with our topic on coastal protection. By transferring sand from one location to another location on the shoreline is basically the concept of beach nourishment. The sand source can come from offshore deposit or deposit in a coastal bay, in the estuaries. They can even come from land quarries or navigational entrance which need to be dredged. The sand properties typically will need to be determined. Usually fine sediments are not preferable for beach nourishment because they can be washed away easily when exposed to ocean wave. On the other hand, coarser material are much more preferred because they are more stable and thus more cost effective. Beach nourishment must be done in such a way that the borrow from the source as well as the deposit on the target site is carried out in such a way that it does not cause any environmental or ecological problem, and also make sure that the sediment used does not contain any undesirable contaminants. This figure here is taken from USACE's Coastal Engineering Manual. It shows that since 1950s until the 1990s, the coastal projects using soft engineering approach is gaining momentum and becomes more popular compared to hard engineering approach. This shows that the engineering community are well aware of the advantages of soft engineering such as beach nourishment. To plan for beach nourishment, some of the considerations include to study the local littoral transport, to investigate the current beach profile and also to design for the new beach profile. The native material and the borrowed material must be well investigated by comparing their grain size distribution. Since the beach nourishment typically is not a one-time project and it requires scheduled maintenance, so a feeder and a stockpile system must be planned such that additional refuel can be carried out as and when it is necessary. Although beach nourishment is by definition a soft engineering approach, it also frequently requires coastal structures such as groin, offshore breakwater and submerged breakwaters, which will need to be designed for accordingly to achieve the most optimum outcome. All beach nourishment will require the estimate of the soil loss over time in order to determine the overfill required and also for the nourishment work to be scheduled in the future. Beach nourishment usually means that the width of the beachfront will be extended, and thus it usually results in a steeper slope compared to the natural beach, which can be supported by using appropriate submerged seal. Allowance must be made that the nourished beach will be reshaped or adjust to the local coastal climate, and so a certain amount of overfill might be provided to allow for the loss of especially the fine material in the field. Also, excess sand can be provided on the updrift end of the beach to act as a constant supply under net littoral drift action. Also, potential seaward loss of the soil during extreme event will need to be estimated, and scour protection at the toe end of the nourished beach must also be provided. Right now we're going to look at the design of beach nourishment. We recall that previously we have introduced the P unit, which is commonly used to describe coastal sediment material. Here we are also going to introduce a few of the statistical properties which are useful for us to describe the sediment material. Most importantly, we will be using P mean diameter, M, which is the average of the P 84% passing and P 16% passing, and the sorting characteristic given by the P deviation measure, sigma, which is the difference between the P84 and P16 divided by 2. We will quantify the sorting value P and the mean diameter M of both the borrow and the material and the native material, so that we are able to calculate the ratio for this expression and this expression. Noting that this expression gives us the idea of the borrow size compared to the native site. If the expression is positive, it indicates that the borrow size is relatively small compared to the native site, whereas when the value is negative, then the borrow size is relatively larger than the native material, which is why if we look at this figure, it is divided into quadrant 1, 2, 3, and 4. The left is basically relatively stable because the borrow size is larger, but the right is relatively unstable because the borrow size is smaller. We're going to use this graph to determine the overfill factor, which is how much fill material is required to produce 1 cubic meter of beach material. It depends not only on this ratio, but also on the ratio of the sorting of the borrowed material compared to the native material. If the value is small, it shows that the borrowed material is relatively well sorted, which means that the size is quite uniform compared to the native. Whereas if the value is large, it shows that the borrowed material is poorly sorted, meaning that it has a larger range of sediment size compared to the native material. So as a result of these two, we are able to locate the RA value, the overfill factor value, from the figure here. All right. So for example, if we get a relative if we get an overfill factor RA of close to 1, for example here 1.05, relatively stable, it means that we only need 1.05 meter cube of borrow to produce 1 meter cube of fill. However, if we move on to this side, you notice that, for example, over here we might need up to 10 meter cube of borrow in order to produce just 1 meter cube of fill, because the material is relatively unstable. Take note that if the material contains a certain percentage of sand, then adjustment will have to be made to the overfill factor to get the modified value. This table here describes the properties of the borrowed material compared to the native material for each of the quadrant. Next, we will determine the renourishment factor R sub j, which can be described by this equation or can be obtained from this graph, which is valid for delta equals to 1. The delta value can range from 0.5 to 1.5, and it represents the scale difference between P means of non-eroding and actively eroding native beach sediments. We notice that the graph is dependent on the same ratios as the overfill factors, and we can read the values of Rj based on the value we know for these two ratios. The stable region here has a renourishment factor of 1 to 50, which is very low, whereas moving on to the right and lower end of the graph, the region here is unstable with nourishment factor of up to 7. The larger the renourishment factor, the more unstable the beach nourishment is. Here, the renourishment factor can be defined as how frequent the renourishment needs to be carried out. Right now, let us look at this example. Here we have the composite native beach material given by phi 84 equals to 2.47 phi and phi 16 equals to 1.41 phi, which correspond to 0.18 mm and 0.38 mm respectively, whereas the proposed composite borrow material has phi 84 and phi 16 of 3.41 phi and 1.67 phi respectively. So first and foremost, let us derive all the statistical properties of both the native and the borrow material. We obtain the M phi value for the native and the borrow. We see that the borrow material has a larger value of M compared to N, meaning that actually the borrow material has a smaller size compared to the native material. Next, we determine the sorting property, which is sigma, and we get the sigma value for the native as 0.53 and the sigma value for the borrow as 0.87. Here the sigma value of the borrow is larger, meaning that the borrow material is poorly sorted. It has a broader range. So not only the borrow material has a smaller size, it also has a broader range of size, which suggests at this stage that the borrow material is not very ideal. However, let's proceed from here. We will now work out the sorting ratio, sigma b over sigma n, which is 1.64, and the p mean difference, which is given as 1.13. So now using these two values, we will obtain the overfill factor Ra from the graph, which is approximately 2.3, and we also obtain the Rj value, the renourishment factor, which is approximately 1.3. So this is what it means. Based on the outcome, the project required 2.3 meter cube of borrow to produce 1 meter cube of fill on site. So we need to place up to 2.3 meter cube, whereby we expect that up to 1.3 meter cube will be lost and only 1 meter cube will remain in the renourished beach. And also, renourishment will have to be carried out at 1.3 times frequency compared to the native material. What does this mean? Let's say if the native material is eroded in such a rate that it needs to be renourished every year, then by using this borrow material, the beach will have to be renourished every 1 over 1.3 year, which turns out to be 9 months. So by using this relatively undesirable borrow material, we actually need to renourish this beach more often than the native material itself. The performance of beach nourishment must be evaluated by monitoring the changes in the shoreline as well as the beach profile over time. This can be done by using periodic survey of the topography of the beach as well as the hydrography, and also using sediment samples, aerial photograph, and if necessary, measurement of the wave field in the area.